Hi friends, welcome to a new lecture on bandwidth utilization. Here is Meezaan Khan on Meezaan TV with computer-generated voice. Before starting the lecture, it is requested to please subscribe the channel and press the bell icon for more videos. The basic knowledge of zero lecture delivered in class is required to understand this lecture. The link of the lecture is listed below and given in description also. Please go through the zero lecture before. As data and voice transmission increases, the burden on networks also increased. In real life, we have links with limited bandwidth. Bandwidth utilization is the wise use of available bandwidth to achieve specific goals like efficiency and anti-jamming. Efficiency can be achieved by multiplexing. Whenever the bandwidth of a medium linking two devices is greater than the bandwidth needs of the devices, the link can be shared. Multiplexing is the set of techniques that allows the simultaneous transmission of multiple signals across a single data link. The process of multiplexing is shown in figure. In a multiplex system, n lines share the bandwidth of one link. The lines on the left direct their transmission streams to a multiplexer, which combines them into a single stream simply refers as many to one link. At the receiving end, that stream is fed into a demultiplexer, which separates the stream back into its component transmissions simply refers as one-to-many link and directs them to their corresponding lines. As shown in the figure, the word link refers to the physical path. The word channel refers to the portion of a link that carries the transmission between a given pair of lines. One link may have n number of channels. There are three basic multiplexing techniques: frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. The first two techniques are designed for analog signals, while the third one is for digital signals. Frequency division multiplexing (FDM) is an analog technique that can be applied when the bandwidth of a link in Hertz is greater than the combined bandwidths of the signals to be transmitted. In FDM, signals generated by each sending device modulate different Carter frequencies. These modulated signals are then combined into a single composite signal that can be transported by the link. Carrier frequencies are separated by sufficient bandwidth to accommodate the modulated signal. These bandwidth ranges are the channels through which the various signals travel. Channels can be separated by strips of unused bandwidth guard bands to prevent signals from overlapping. In addition, carrier frequencies must not interfere with the original data frequencies. The demultiplexer uses a series of filters to decompose the multiplex signal into its constituent component signals. The individual signals are then passed to a demodulator that separates them from their carriers and passes them to the output lines. This is the most important example for both course and job perspective also. Here in this example there are 5 channels each with 100 kHz band. Since the total bandwidth of the channels are 500 kHz, the guard band is 10 kHz. Since there will be 4 guards between 5 channels, the bandwidth required for guard band is 40 kHz. The total bandwidth of the multiplex link will be 500 plus 40 equals 540 kHz. Wavelength division multiplexing WDM is designed to use the high data rate capability of fiber optic cable. Using a fiber optic cable for one single line wastes the available bandwidth. Multiplexing allows us to combine several lines into one. WDM is an analog multiplexing technique to combine optical signals. The combining and splitting of light sources are easily handled by a prism. Recall from basic physics that a prism bends a beam of light based on the angle of incidence and the frequency. As shown in figure, using this technique, a multiplexer can be made to combine several input beams of light, each containing a narrow band of frequencies, into one output beam of a wider band of frequencies. A demultiplexer can also be made to reverse the process. One application of WDM is the SONI network, in which multiple optical Fiber lines are multiplexed and demultiplexed. A new method, called dense WDM/DWDM, can multiplex a very large number of channels by spacing channels very close to one another. It achieves even greater efficiency. Time division. Multiplexing (TDM) is a digital process that allows several connections to share the high bandwidth of a link. In TDM, time is shared. Each connection occupies a portion of time in the link. Note that the same link is used as in FDM. Here, however, the link is shown sectioned by time rather than by frequency. In the figure, portions of signals 1, 2, 3, and 4 occupy the link sequentially. TDM is a digital multiplexing technique for combining several low-rate channels into one high-rate one. We can divide TDM into two different schemes, synchronous and statistical. In synchronous TDM, each input connection has an allotment in the output, even if it is not sending data. In synchronous TDM, the data flow of each input connection is divided into units, where each input occupies one input time slot. A unit can be one bit, one character, or one block of data. Each input unit becomes one output unit, and occupies one output time slot. However, the duration of an output time slot is n times shorter than the duration of an input time slot. If an input time slot is t seconds, the output time slot is t by n seconds, where n is the number of connections. In other words, a unit in the output connection has a shorter duration, it travels faster. In synchronous TDM, the data rate of the link is n times faster, and the unit duration is n times shorter. TDM can be visualized as two fast rotating switches. One on the multiplexing side and the other on the demultiplexing side. The switches are synchronized and rotate at the same speed, but in opposite directions. On the multiplexing side, as the switch opens in front of a connection, that connection has the opportunity to send data onto the path. This process is called interleaving. Same process, but at the opposite direction take place at demultiplex side. Synchronous TDM is not as efficient as it could be. If a source does not have data to send, the corresponding slot in the output frame is empty, which causes efficiency. This is another important example. The figure shows the multiplexer. Here in this example there are 4 channels each with 100 bytes per second are multiplexed. Each frame carry 1 byte from each user, since the frame size is 4 byte or 32 bits. Now each channel rate is 100 bytes per second. The frame rate is 100 frames per second. The data rate is 100 frame, multiply by 32 bits equal to 3200 bits per second. This is another important example. The figure shows the multiplexer. Here in this example there are 4 channels each with 100 kilobits per second. Each frame carry 2 bits from each user, since the frame size is 8 bits. Now each channel rate is 100 kilobits per second. The frame rate is 50 kilo frames per second. The data rate is 50 kilo frame, multiply by 8 bits equal to 400 kilobits per second. The frame duration is 1 by 50 kilo or 20 microseconds. The bits duration is 1 by 400 kilo or 2.5 microseconds. The main problem with TDM is how to handle a disparity in the input data rates. In all our discussions so far, we assumed that the data rates of all input lines were the same. However, what to do if data rates are not the same? 3 strategies, or a combination of them, can be used. We call these 3 strategies multi-level multiplexing, multiple slot allocation, and pulse stuffing as shown in figure. Multi-level multiplexing is a technique used when the data rate of an input line is a multiple of others. For example, in figure, we have 2 inputs of 20 kbs and 3 inputs of 40 kbs. The first 2 input lines can be multiplexed together to provide a data rate equal to the last 3. A second level of multiplexing can create an output of 160 kbs. Sometimes it is more efficient to allot more than one slot in a frame to a single input line. For example, we might have an input line that has a data rate that is a multiple of another input. This method, also known as multiple slot allocation, is shown in figure. The input line with a 50 kbs data rate can be given 2 slots in the output. We insert a serial to parallel converter in the line to make 2 inputs out of 1. Sometimes the bit rates of sources are not multiple integers of each other. Therefore, neither of the above 2 techniques can be applied. One solution is to make the highest input data rate the dominant data rate, and then add dummy bits to the input lines with lower rates. This will increase their rates. This technique is called pulse stuffing, bit padding, or bit stuffing. The input with a data rate of 46 is pulse stuffed to increase the rate to 50 kbs. Now multiplexing can take place. Synchronization between the multiplexer and demultiplexer is a major issue. If the multiplexer and the demultiplexer are not synchronized, a bit belonging to one channel may be received by the wrong channel. For this reason, one or more synchronization bits are usually added to the beginning of each frame. These bits, called framing bits, follow a pattern, frame to frame, that allows the demultiplexer to synchronize with the incoming stream, so that it can separate the time slots accurately. In most cases, this synchronization information consists of 1 bit per frame, alternating between 0 and 1. As we saw in the previous section, in synchronous TDM, each input has a reserved slot in the output frame. This can be inefficient if some input lines have no data to send. In statistical time division multiplexing, slots are dynamically allocated to improve bandwidth efficiency. Only when an input line has a slots with data to send is it given a slot in the output frame. In statistical multiplexing, the number of slots in each frame is less than the number of input lines. The multiplexer checks each input line in round-robin fashion. It allocates a slot for an input line if the line has data to send. Otherwise, it skips the line and checks the next line. The output slot in synchronous TDM is totally occupied by data. In synchronous TDM, there is no need for addressing. Synchronization and pre-assigned relationships between the inputs and outputs serve as an address. While in statistical TDM, a slot needs to carry data as well as the address of the destination. Furthermore, there is no fixed relationship between the inputs and outputs, because there are no pre-assigned or reserved slots. 3 important terms should be considered when using statistical TDM. 1. Ratio of data and address bits. Since a slot carries both data and an address in statistical TDM, the ratio of the data size to address size must be reasonable to make transmission efficient. For example, it would be inefficient to send 1 bit per slot as data when the address 3 bits. Second is, the frames in statistical TDM need not be synchronized, so we do not need synchronization bits. Third is, the capacity of the link is normally less than the sum of the capacities of each channel. The designers of statistical TDM define the capacity of the link based on the statistics of the load for each channel. If on average only X% of the input slots are filled, the capacity of the link reflects this. Therefore, during peak times, some slots need to wait. I think this is enough for today. In the next lecture, we will discuss about the spreading techniques. Please subscribe the channel and press the bell icon for more videos. Thank you for watching.